Okay, so how is everyone today? Good, I hope. All right. So last time we had talked about linear models. And to recap, the main idea is just, well, you have a question?
I do. Are you going to take questions today on...
Over linear models?
No, well, it was the online homework.
I need you to ask me after class, because the amount of things we have to do today is a lot. But I'll be glad to help you after class. It's the best I can do.
Okay, one more question.
Uh-huh.
When we have homework questions, what's the proper way to ask? Because I sent an email to you, but I didn't know if that was something that we're not supposed to do.
No, it's fine. You can email me. The best way is email, but sometimes my email is backlogged. Like right now, I'm working through getting it backlogged, so it can take a while. The very best thing, if you want my personal attention, is to ask me to see you after class.
So, because I have another class after this, and I have a quiz.
I appreciate that.
So
I'd be happy to, after the lecture is over, we can arrange some time that's after that class.
I have another class after that class.
Okay, I have to continue, but
No,
what I'm telling you is that you can ask me after the lecture is over, and we can arrange something. Okay?
I'll look at your office hours on the syllabus.
Okay. Other questions? Okay, so last time we were talking about linear models. The main idea is that somehow you have a word problem, and two quantities are said to be linearly related, and then the numbers can be sort of arbitrary. Then you, one way or another, use the point-slope equation for a line, and then solve for one of the variables. And the numbers usually end up getting crazy. Like from the example last time, one of the numbers was like 1,700,000, whatever. Okay, but the craziness of those numbers, that's just a fact of life. That's just how it ends up working out. Okay, so fine. We need to move to the next thing. So I had promised a discussion about fractions and adding things up, adding fractions up. So here's that discussion. So let A, B, C, and D be in the reals, and let B not be 0, and D not be 0. So, good. Here's the first case, is that A over B plus C over B. So what I want you to take note of is that these two are the same, these two denominators. Okay, so they're the same. When you're dealing with fractions, the denominator is in some ways like the type, like the kind of thing you're dealing with. So what I'm telling you is that this kind of question is like when you were in second grade in Miss Harris's class, and the question was, if you have A apples and then you get C more apples, how many apples do you have? Well, you have A plus C apples. A apples added to C apples is A plus C apples. So that's how it works. Now, the reason why it works this way, and not some other way, is the following. Well, A over B plus C over B. Concerning just that first term there, A over B, at the present time, b is in the denominator. Is there some way we could write something that's equal to that, but there's not a b in the denominator? Okay, so
Be a negative also?
there's going to be something about negative, yes.
So it's not negative b over a?
No.
Okay. Is it to a power?
Yeah, b is going to have an exponent.
So b to negative minus 1 and 1.
B to negative 1. So this would be b to negative 1 multiplied by a. So what I'm saying is that a over b is the same as b to negative 1 multiplied by a. Now, I want to do a similar thing for this term. What will we write this one for as? Right. So now, this is b to negative 1 multiplied by c. What I want you to observe now is that these two terms share this factor. Right? B to negative 1 is a factor in that term. B to negative 1 is a factor in that term. As a result, we can factor out b to negative 1. And if we factor out b to negative 1, then what do we need to write in those parentheses? A plus c. But then, you know, after all, I don't really like writing b to negative 1. I'd rather write it some other way. Is there some other way we can write b to negative 1? In the denominator, right? But that's exactly this. So what I'm telling you is that when you do this, right, this is something you should memorize, because otherwise you got to take the long way around. It's kind of, you know, everybody likes shortcuts. Good. Any question about that?
When you said that's something you should memorize, you mean the first piece of a plus
This.
b over b. Okay.
Yeah. So, for example, what I'm saying is that if I were to ask you, like, say, 2 over 5 plus 14 over 5. So observe that the denominators are the same. So this is like 2 apples plus 14 apples. So how many? 16, right? 2 fifths plus 14 fifths is 16 fifths. Any question about this one? Okay. Fine. It also works with variables. So something like, say, 3 over x plus 4 plus x plus 7 over x plus 4. So do you observe that this is, again, two fractions, and they have the same denominator? So that means we can add the numerators, and what do we get in the numerator?
Plus x plus 7.
Right, 3 plus x plus 7 over x plus 4. I guess those bottom parentheses weren't really necessary. And then, of course, you can simplify this to x plus 10 over x plus 4.
This may be irrelevant. Is that middle intermediate step necessary?
No.
We go straight to the next?
Yeah, straight to the end. Okay, good. 2. So now, suppose we have a over b multiplied by c over d. So now I want you to observe that the denominators are different, but not only are the denominators different, the operation is different. We changed the operation from plus to multiply, right? From add to multiply. Okay, well, this is equal to AC divided by BD. Okay, so I'll give it just a brief example. So, for example, say, what is 13 over 14 multiplied by 20 over 18? Well, this is the product of two fractions, right? One fraction multiplied by another fraction. What would be the numerator? 13 times 20. And what would be the denominator? 14 times 18, right? And then, well, you know, I'm not going to worry about it here and now, but usually there's some kind of request to please go on to simplify your answer. Okay, but I'm not going to worry about that here because we have other things to do. This works just as well with variables. So, for example, x over x squared plus 1, and then this multiplied by 3x plus 4 over, I don't know, 10. So it works just as well. Okay, what will the numerator be? Okay, so it'll be the product of the numerators. So now I'm going to write something, and it is not correct. So x over 3x plus 4, and x squared plus 1 multiplied by 10. Okay. Now what's wrong with this? Oh, distribute? What do you mean? It's x squared plus 1 multiplied by 10, right?
No, the numerator, you've got to distribute the x amongst the entire numerator on the second fraction.
Okay.
So according to PEMDAS, then you have to do that.
Right. Consider the numerator, for example. This x right here, that corresponds to that x right there. We want this x to multiply the whole 3x plus 4. What is it currently multiplying?
Just the 3.
Just the 3, right? Because multiplication has a higher precedence than addition. So it's only multiplying the 3. So to make this right, you parenthesize the 3x plus 4. And what do we need to do to make this one right? Because notice, at the present time, this 10, we want the 10 to multiply all of x squared plus 1. At the present time, what is 10 multiplying? Just the 1, and not the x squared. So, like so. Now it's right.
Would it be right if you put the parentheses around the 10 and not the x squared plus 1?
I think the question is it the case that x squared plus 1 multiplied by 10 is the same as this? It is not.
Okay.
Because, well, still, the parentheses say you've got to figure out what this is equal to first. Well, it's equal to 10. And then after you've done that, you have to choose between doing a multiplication or an addition. Well, you do the multiplication. So the 10 is not multiplying the x squared.
Even if the multiplication dot was not there? If you just had x squared plus 1 parentheses 10? And
Even still, because the when you write things side by side, like x, y, the dot is understood. Good. 3, item 3. Okay, so now we have a over b plus c over d. So now I would like for you to observe that this one is like 1. It's like item 1 in the sense that we're adding two fractions. But how is it different?
denominators are not different.
Right, the denominators are not the same. So this is like 1, but the denominators are not the same. Okay, so again, sort of loosely interpreting denominator as a type, as a kind, it is like requesting we have A apples and C giraffes. So altogether, how many do we have? How many? You know, it doesn't make any sense. You can't add apples to giraffes. Okay, but that analogy kind of breaks down a little bit because these are numbers, we really can do something. The work that we have to do is we have to take this, so these do not have the same denominator. We need to perform a little bit of work until they do have the same denominator. The punchline is that the answer is A multiplied by D plus B multiplied by C divided by B multiplied by D. So that's the punchline. We're going to demonstrate why that's the case, but that's the punchline. This is referred to as the cross-multiply formula. Or if your previous math instructor was a little bit artsy, it might have been referred to as the butterfly formula. Either one is fine. The reason for that name is that if you take these two, so A over B, plus C over D, and write what it's equal to, AD plus BC over BD, then observe. On the right-hand side, if you circle the AD, so there's the AD. If you circle the AD on the left-hand side, then you get this. That's AD. If you circle the BC on the right-hand side, there it is. And when you circle it on the left-hand side, it's that. For this reason, that's why it's called the cross multiplication formula. If you go on to circle the BD on the right-hand side, and then circle the BD here, and if you kind of squint your eyes and do a lot of hoping, that might look like a butterfly to you. Any question about the formula or its name? So let's see why that formula is correct. Yes?
The formulas prior to this that you did, do those have names?
They do not. No names that I am aware of. Okay, so the reason for the reason why the cross multiplication formula is correct is the following. So we want to take A over B plus C over D, and we want to add them together. But the thing that we have to overcome is the fact that the denominators are, at the present time, not the same. This one's denominator is B, and that one's denominator is D. Okay, so I'm going to take that A over B, and I'm going to multiply it by, well, 1. That's the only thing you can multiply it by and not change its value. I'm going to do the same thing for C over D. I'm going to multiply it by 1. The real trick to understanding how this works is that you've got to figure out a nice way to write 1. So, for example, I just literally wrote a 1 right there. But 3 over 3 is also equal to 1. And so is 33 over 33. And 7 over 7, and there's a lot of ways to write 1. Okay, so then A over B multiplied by, now, comparing these two, this one has a B in its denominator. The first one has a B. And compared to the second one, which has a D, I'll say that the first one is kind of missing a D in its denominator. Wouldn't it be nice if it had a D? Well, let's just give it a D. There. Now you have a D. But what's the cost of putting a D in the denominator? Also putting it in the numerator. And what I want you to observe is that that red 1 is that red 1. D over D is 1. Okay. Plus C over D multiplied by... So, the red one we wrote as D over D. How are we going to write the green one? B over B. Okay, that's also equal to 1. So we haven't changed anything. Everything is still equal. But because of item 2, this is the product of two fractions, we can rewrite that how? AD over BD. So AD over BD. And how can we rewrite that one? CB over DB. But instead of writing the numerator as CB, which is fine, I'm going to commute it and instead write it as what? BC. So this will be plus BC in the numerator over. Now, you know, if you look at the formula directly, it was DB, but I'll commute that to what? BD. And now what pleasant circumstance do we find ourselves in? Yeah, now we're trying to add two fractions, and now the denominator is the same. So the answer is AD plus BC over BD. Okay. So let's use it in an example. So how about 5 over 7 plus 10 over 9. So those denominators are not the same. So you can't add them directly. You've got to do a little bit of work. Well, we could use the cross multiply formula. So using the cross multiply formula, there's three things. What goes in the top left? Very good. What goes in the top right? 10 times 7. And what goes in the denominator? 7 times 9. 9. It all worked fine in my head until the 9 got lost. I wrote a D. Okay, so that's a direct substitution into the formula. Okay. Well, 5 times 9, that's 45. 10 times 7, that's 70. 7 times 9, that's 63. So that would be 115 divided by 63. Any question about this one?
And there's, that's okay to leave it in that form.
Yes. I think maybe your question is, does it simplify any further?
Even if yes, and then if it did, would we have to?
So two questions. Does it simplify further? No. It doesn't. Second is that, suppose that it did, would I want you to? In such a case, if I don't say to, please don't. And then if I do, please do. If I do say so, please do.
And then isn't it the case that there is a possibility that 7 and 9, in this case they don't, but there might be a denominator, a common denominator that would be easier?
That's what we're going to talk about now.
Okay.
But I have to say one thing in between. So doing it this way, this is just straight using the formula. It's a fine way to do it. That's not the way I do it in my head. So I noticed that I don't know, like half of you do it a slightly different way. So I'll show that way also. So 5 over 7 plus 10 over 9. The way it works in my head is I look at these two fractions and say, okay, well, they don't have the same denominator. So in a sense, this one's denominator is missing what? A 9. So I'll multiply this 5 over 7 by 9 over 9. If I do that, multiply by 9 over 9, what's the new numerator? 45. And the new denominator? 63. As for the second fraction, what's its denominator missing? A 7. So I'll multiply it by what? 7 over 7. What's the new numerator? 70. And the new denominator? 63. And then, oh, great. Now they're the same kind of thing, right? They have the same denominator, so the answer is 115 over 63. Okay. At any rate, that's the way it works in my head. Feel free to take either route. Well, here's an example concerning something that you already know, and I'll title this example the greatest common divisor least common multiple and common denominator. Okay. So, in the first place, I want you to observe the following, that we could do something like this. We could say, well, how about please add 7 over 12 plus 13 over 16. Okay, so are the denominators the same? No, so we're going to need to do a little bit of work. Do you want to do it? I don't care. Do you want me to do the cross multiplication thingy, or do you want me to do this one? Doesn't matter to me. First one or second one?
Second would be shorter.
Second one? Okay. Well, so this one has a 12, and it's missing a 16. So I'll multiply this one by 16 over 16. I need a calculator for that. So multiplying the first one by 16 over 16, the numerator is 112. The denominator is 192. That's the first fraction. Now, concerning the second fraction, what is its denominator missing? A 12. So what will I do in response? Right, so I'll multiply it by 12 over 12. The numerator will become 156. Its denominator will again be 192. And this is a nice situation to find yourself in because now the fractions have the same denominator and the numerators can be added. So it will all be over 192. And then it'll be 112 plus 156, 268. Okay, but in such an exercise, let's go on to suppose that the instruction stipulated that you need to simplify your fractions so that the numerator and the denominator don't have any common terms, common factors. Well, I don't know, I can't really tell. It appears to me that 268 is divisible by 2. So that would be 134 over 192 is divisible by 2. 96. But they're both still divisible by 2, so I've got to go a little further. 134 over 2 would be 67, and then over 48. And then now those numbers are small enough that I can get it figured out. The only primes that divide 48 are 2 and 3, and 2 and 3 don't divide 67. So that's as far as it goes. Okay. Now, here's the thing. The state of Texas tells me that you are familiar with the following. So the phrase is greatest common divisor and least common multiple. Is that given given A and B in the naturals, that is to say positive integers, it is the case that A multiplied by B is equal to the GCD of A and B multiplied by the LCM of A and B. So the product of two numbers, A and B, is actually the product of their greatest common divisor and their least common multiple. The state of Texas says that I don't even need to mention this because you know it. But they've been known to be mistaken from time to time. So using this in an example. What is the GCD, the greatest common divisor, of 12 and 16? That is to say, I want a number, an integer, that divides both of them, and it's the greatest of all such. 4, right? So 1 divides both of them, but is that the greatest integer that divides both of them? No, right? Because 2 divides both of them. Is that one the greatest one? No, it's 4, right? So the answer is, the GCD is 4. As a result, you can compute the least common multiple in the following way. The least common multiple of 12 and 16 is, well, you can take this equation up here and solve for LCM. It's saying that the least common multiple of 12 and 16 is 12 multiplied by 16 divided by the GCD of 12 and 16, yes. We just established that the GCD of 12 and 16 is 4. So the least common multiple of 12 and 16 is 48. So 12 times 16 over 4 is 48. So now, what's the interpretation of that of the least common multiple? What it's saying is that, well, consider the numbers 12 and 16. Consider the numbers 12 and 16. Now, 12 would divide 12 times 16. So in particular, it divides 192. And 16 also divides 12 times 16. It also divides 192. But the question is there some number that's smaller than 192 that 12 and 16 both divide? Well, let's consider. What if we take 2 12s? How much is 2 12s? 24. Does 16 divide 24? No, that doesn't work. What if we take 3 12s? 36. Does 16 divide 36? No, that's not going to work. What if we took 4 12s? How much is 4 12s? 48. Does 16 divide 48? Oh, it does. So 12 divides 48, and 16 also divides 48. They both divide 48. Because they both divide 48, that is a smaller number than 192, and it makes the arithmetic a little nicer. As a result, we could do the following. We could say, okay, 7 over 12 plus 13 over 16, the same request as before. Now, as an aside, I ask myself, what is the least common multiple of 12 and 16? You can always do it this way, product divided by greatest common divisor. That always works. But a lot of times the numbers are small enough to where you can just figure it out in your head. One way or another, you establish that the least common multiple is 48. And then you say, 48 is the denominator that I want. So for this fraction, at the present time, the denominator is 12, but we want it to be 48. What do we need to do to make this one have a denominator of 48? 4 over 4, right? If we multiply by 4 over 4, the denominator would be 48, and the numerator would be 28. Similarly, this fraction, its denominator is 16, but we want its denominator to be what? 48. What do we need to multiply that one by to achieve a denominator of 48? 3 over 3. So that would be 39 over 48. And then, oh look, they're both over 48. So nice. You add those together and you get 67 over 48. So there's two nice things about doing this kind of computation in this way. One of the nice things is that it can often be a little bit shorter. Another nice thing is that you don't have to simplify after the fact. It will already be simple. Okay, so notice that when you just sort of do it in the blind cross multiply way, you've got to end up doing some simplification. This is sort of like saying that, oh, I already know I'm going to have to simplify it, and I'm just going to just do it all in advance. So this is, in a sense, establishing what the denominator will be in advance. Any question about this? Okay, so let's do it now with variables. So, for example, suppose we ask, okay, what is 3 over, I don't know, 3 over 4x plus 5, and then to that we want to add 6x minus 7 divided by x plus 8. So we want to add these two fractions. Now it's a little bit intimidating, slightly, because there's variables. It was nicer when it was 5 over 7, right? But everything's the same. All the strategies are the same. You just ask, are these two denominators the same? They're not. They're not the same. So we could use the cross multiply formula. Okay, so I'll use it. So the cross multiply formula is one big fraction. So what's going to go in the denominator? Okay, good. 4 times x plus 5 multiplied by x plus 8. Now what's wrong with what I've written? It's not parenthesized. Okay. And what goes in the top left? 3 multiplied by x plus 8. What goes in the top right? Right, correct. So 6 x subtract 7 multiplied by 4 times x plus 5. Okay, we've got to do one more, and then we'll have a quiz. In a normal exercise, I would say, and multiply it out and collect like terms. But we need to do one more thing before the quiz. So, what about something like this? 3 over w plus 4 multiplied by w plus 6, and then plus, I don't know, 7w minus 4 divided by w plus 4 multiplied by 2w plus 5. So now, in one sense, this question is just like the one immediately above it. You could use the cross multiply formula, and it would work. But if the instructions say and simplify, it's going to get outrageous. Okay. What I want you to observe is that in the two fractions I'm asking you to add together, do you observe that they both have a w plus 4 in their denominators? They both have it. Similarly, this one only has a w plus 6, so that one's missing a w plus 6. What is this one missing?
2w plus 5.
A 2w plus 5. So, in the end, what we need is the denominators to be the same. So as for that first fraction, it already had a w plus 4 multiplied by w plus 6. And what was it missing? A 2w plus 5. So here you go. I happen to have one laying around. But what's the cost of putting the 2w plus 5 right there? It must also go in the numerator. So do you observe that concerning these red edits I've made, they cancel? That's a fancy way to say do nothing. Okay, as for the other one, 7w subtract 4 in the numerator divided by, it already had a w plus 4 multiplied by 2w plus 5. And what is this one missing? It's missing a w plus 6. So here you go. I happen to have a w plus 6 right over here. But what's the cost of putting the w plus 6 there? Putting it also in the numerator. And here is, again, for the third time today, because 3 is the magic number in teaching, what am I forgetting? Parentheses. Now the denominators are the same. What we did here is analogous to the least common multiple. Just figure out just what this one was missing. This one was missing just a 2w plus 5. And this one was just missing a w plus 6. In the same way that a 12 was just missing a 4, and a 16 was just missing a 3. Okay, so now we have to have a quiz.